these guys may just end up getting a high count regardless because they're just close together, and you may just end up sequencing. There are some corrections that the protocol actually does in order to avoid these kinds of things. But you have a strong distance dependence, meaning that you tend to observe very high count between pairs of regions that are close together. And the expectation is that the counts decrease as the distance of two regions increases, but then that's what the null is. And then one compares pairs of regions compared to that expected count at a particular distance interval and says, are you an interested region to pair of regions to interact? Does that make sense?
Yeah.
So what those matrices are doing is basically taking the chromosome in this form and then telling you whether this region is close to this other region. So in linear space, this region is actually very far away from this region, but in three-dimensional space, this region and this region are much closer together. And the corresponding entry count in that matrix will be high. Okay? But then it can be looping together in many complicated ways, and actually groups of regions can loop together and form what are these domains, and that's what we actually try to find out. Okay? So if you think of each of those, you could think of this as, in the most simple form as a 3 billion dimensional matrix, right? Because there are 3 billion bases. But we don't have that level of resolution, meaning the matrix is very, very sparse. So usually what people do is they take the genome, chunk it into bits of, say, the highest resolution is actually 1,000 bases. But people usually, if they're looking at interchromosomal interactions, it's typical to use 100 kilobase regions, or 500, or even 1 megabase regions. So there are not a lot of entries, but it is a reasonably big matrix. And so if you look at like a small portion of this matrix, each of these entries corresponds to a piece of DNA which is of a particular size, and the entries correspond to the count, the tendency of two regions to actually interact. And we can represent that as a graph where the edge weights correspond. So you can say that it's a fully connected graph. Well, many of the counts actually will be zero, so it's not actually fully connected. And we have a graph, and then we can apply graph clustering to it. Okay. Where is my pointer? There it is. Okay. So again, we want to. So we think of this as a graph, and we applied spectral clustering. So spectral clustering here is again the same thing. We've seen this many times, and what we get out are basically partitions along this dimension. So these are all k, and then you have how many other genes in each of these different clusters. We are basically partitioning the matrix in this way, horizontally. So what this picture is telling you is, so one could just take this matrix and apply a standard clustering algorithm. And we did that. And what you see here is what happens if you were to apply algorithms like hierarchical clustering or k-means clustering compared to spectral clustering. And what each of these different columns correspond to are basically how do we say two regions are, like what is their similarity or distance. So we looked at Euclidean distance. So I think, I don't remember this, but maybe you remember it, but the Euclidean distance was calculated by taking two regions and then looking at the count profile and computing the Euclidean distance between those two vectors. That's what we did, yeah. You could also use the Pearson's correlation, Spearman correlation. You could also use just the contact count between, so you take the matrix, you have two regions, and you just look at the count. That also, so all of these clustering algorithms all they really need are pairwise distances / similarities. Okay? All of them work by, that's all they need. And so you can slightly change, actually k-means has a way, a hook in which you can actually give it a pairwise distance matrix, and you can actually do the clustering for you. Instead of just giving you the sample or the object objects by the attributes. So to assess how well the different algorithms did, we use something called silhouette index. So silhouette index is a way to assess the quality of any clustering algorithm. So what do we want a good clustering algorithm to do? A good clustering algorithm should be able to partition our objects, in this case our DNA regions, such that the regions that are within a cluster have a lot of connections or have high contact counts, and regions that are between two clusters have fewer connections. And silhouette index gives you a way to assess the goodness, and it also corrects for over-clustering as well as under-clustering. Okay? So if you are under-clustering, you will have a low number. It's a number between -1 and 1. And if you're under-clustering, you will have a low number. If you're over-clustering, you will have a low number. So the higher the silhouette index, the better you are. Okay? And intuitively, what it is actually doing is it's saying, okay, I have this region. What is my difference from the mean of the cluster to which I belong? And it compares that to the next best cluster that it could have belonged. And it's trying to look at the difference between these two clusters that could have belonged. So it's kind of looking at the boundary of the different clusters. How short are those boundaries? Okay? So what do we see here? And these numbers basically correspond to the rank of the method. So the higher the rank, the better. So overall, what we saw was spectral clustering sometimes can work really well, but sometimes it can be bad. But it seems like it's a reasonable method. So it does depend on the particular distance metric that you're using. However, it is the second competing method compared to the hierarchical clustering algorithm. So as far as silhouette index is concerned, hierarchical clustering seems to be the best algorithm. Here, it seems like graph clustering may not be the best thing to do. However, compared to a standard k-means algorithm, there may be some advantages of the spectral clustering algorithm. Okay? So that is just looking at how good the clusters are, but we have additional data. So when we have clustering, I don't remember if we talked about this, but when you have clustering results, you can assess them in two ways. One is you can say how good are the quality of the clusters, and the second thing that you can do is you can use some external data, and you can say how consistent are the clusters with that external data. And in our case, this external data are basically things like histone modifications or chromatin modifications that occur on the DNA, and the idea is that if our clusters make sense, one should be able to explain some of the one-dimensional signals that we see on the DNA. Okay? And so, so that was silhouette index, but we didn't only use silhouette index, we used other metrics like this DB index, delta contact count, the number of enriched clusters. So this is an external validation metric. And overall, what we found was, and so these are the different external data sets that we use. So each of these are actually one-dimensional signals that are have some information, or the chromosomal contact count data has some information about these signals. And all we are trying to say over here is the groupings that we get using our spectral clustering, does that explain any of these signals? And these are our different clustering algorithms, and the more red a particular entry, the better is a particular, the better the particular method. And what we do is we summarize all of this information in this figure, and basically the higher, the better you are. When we look at all of these metrics together, our overall conclusion was it is actually hard to say whether spectral clustering is actually giving you a clear advantage. However, when we look at the clusters by eye, they seem to do much better. So it's a reasonably good method and has some advantages in terms of exploiting the topology of the graph. Okay, so when you look at a whole bunch of different metrics, this kind of summarizes everything. And this is basically saying that overall rank across all of the different methods, all of the different metrics that we used, it seemed like the spectral clustering overall seemed to have a lower rank compared to all of the other methods. So if you want to use hierarchical, it would look good using one metric. If you use k-means, it would look better using some other metric. And these are the different distance functions that we used, and these numbers we get based on the different metrics that we had. So the Davis-Bouduin, I can't pronounce that word, but silhouette index and number of enriched clusters, all of that together aggregated will give you a number, and we found that in general the spectral clustering method sometimes could be bad, but sometimes it would give you a pretty good result. Okay. So we were actually doing this at a very coarse level, and so this the result of this is going to give you very higher, very coarse level types of organizational units. And actually the most naive result that you would get is basically the chromosomes. So we are taking the entire genome and then we are going to cluster it. However, we don't see that all the time. So what you're seeing here is, again, our contact count matrix, and there were 10 clusters. And what you're seeing here, so each of these black lines correspond to the cluster partitions. Okay, and you see that, you can see that some of these clusters are, so this is clearly a cluster, this is clearly a cluster. And what you're seeing here is the composition of this cluster in terms of the chromosomes that it captures. So there are some clusters that just correspond to one chromosome or chunks of chromosomes. However, the majority of the clusters actually have components from many different chromosomes. Which is interesting. Yeah.
Is it believed that that is biologically meaningful, or is it just sort of that stuff is crammed together so that
it's hard to know, and I mean we don't know what our truth is. We just can only use different analytical measures to say this is what is. The point was that the clusters are not just driven by the chromosomes. One thing that people have seen is this notion of territories, where different chromosomes just come together and then different regions interact. So like chromosome 19, 20, 21 tend to interact together and clump together. And we think that maybe some of them may be capturing something like chromosomal territories. But this is at a very low resolution, so it's kind of hard to say how biologically interesting it is. This is what the data is. One thing that I can tell you, so again, what do we do? Well, we again looked at whether these regions actually, these clusters are meaningful in any way. And so what you're seeing here are, so to get to John's question of whether there's anything biologically interesting happening in terms of these different clumps together, what you're seeing over here are, again, different, so these are histone modifications that measure how active a particular region is or how repressive a particular region is. Most of them are how active. These are different transcription factors, but we also had these signals which are called repeat elements, so sign, transposable elements, and you can actually get genome-wide tracks. So you know which region is a sign or a line. These are like how long or how big, how short these different repeat elements are. And what we wanted to see was whether any of our clusters are significantly enriched for these different types of elements. And what we found was largely there were really two types of clusters that tended to have these guys, and then clusters that tended to have, didn't have these guys, but had a greater tendency to see, what was it, like this one, what is this? The LAD. So not all of them are discriminative, but there is a general tendency to find, to clusters that have these marks versus